Trapezoidal Approximation Method. Before we move on, let's remind ourselves of the area of a trapezoid formula. So the formula for the area of a trapezoid is 1/2 times the height times the quantity base 1 plus base 2. So you might be used to thinking of a trapezoid shaped in general like this. So where this might be base 1 and this is base 2, and then the vertical portion is defined as the height. But we're actually going to be dealing with trapezoids sort of on their side. So the height is going to be along the x-axis, and base 1 and base 2 are going to be found by using function values. So we're still going to be using the area of a trapezoid and this formula, but our trapezoids are going to be, in general, of this form. Now we're still trying to approximate the area bounded by the curve f of x and the x-axis, but now we're going to use trapezoids. So let's just take a quick look at this function here. So here we have f of x, and we're using trapezoids here to approximate the area under the curve. So if you can see, sort of just by looking, it's a pretty good approximation with only using 3 trapezoids. So that's sort of the motivation behind using trapezoids to approximate area. It's a pretty good approximation, in this case with just 3 trapezoids. So you can tell it's a bit of an over approximation. So we have this extra area in each of the 3 cases of the trapezoids, but it's still pretty good. Some things just to note is that we still want to consider n number of objects. So in this case, n is going to be the number of trapezoids. And we still do have this concept of delta x. So delta x, the formula for delta x is going to be b minus a over n, where n is the number of trapezoids. B and a are the endpoints, so we're still going to have this concept of endpoints, and that stays the same. And delta x is going to represent, really in the formula for the area of trapezoids, it's going to represent the height. So delta x is going to correspond to the h in the previous formula that we just took a quick look at. So now let's go ahead and jump into an example. Alright, so in this example we want to approximate the area under f of x equals the square root of x function on the interval from 1 to 5 using 4 trapezoids. So the number of trapezoids given is 4, so our n value is 4. And we can also determine the height of each of our trapezoids by using the delta x formula here. So delta x is going to be b minus a, so 5 minus 1, over 4, the number of trapezoids. So 5 minus 1 is 4. 4 divided by 4 is 1. So I'm going to have a height of 1 for each of my trapezoids. But remember that the height lies on the x-axis. So we're looking at what's going on between 1 and 4. Or I'm sorry, 1 and 5. We're looking at what's going on between 1 and 5. And so each of the height is going to be of equal partition 1. So over the first little width, over the first little interval, in order to determine what the trapezoid is going to be, at the very left point of the subinterval, I'm going to go up to the function. And then on the very right point of the subinterval, I'm going to go up to the function. And then I'm going to connect those two function values and then complete the trapezoid to draw the first trapezoid in my approximation. So to draw the second one, well, I already have 1 point drawn. So at 2, I go up to the function and construct f of 2. So now, if I go to the rightmost point, I go up to the function. And then I connect those 2 points, f of 2 and f of 3, with a straight line. And then complete the trapezoid with my vertical lines down. And that's going to be my second trapezoid. So between 3 and 4, I'm missing f of 4. So I connect f of 3 and f of 4. And then draw my vertical line. And then finally, my last trapezoid is going to be found by finding f of 5 and connecting f of 4 and f of 5 with a straight line and making my last trapezoid. So now, let's write down each of these function values. So this is going to be f of 1. This one's going to be f of 2, f of 3, f of 4, and f of 5. So if we call the function y equals f of x, then this is also considered the point y of 1, y of 2, y of 3, y of 4, and y of 5. So now what I want to do is I want to write the expanded version of the approximation of the area I'm trying to find. So we do use a little shorthand notation for this. We were trying to find T4, the trapezoidal approximation with 4 trapezoids. So let's go ahead and think about the very first trapezoid here. So the area of a trapezoid was 1/2 the height, well the height is 1, times base 1 plus base 2. So base 1 is y1 plus base 2 is y2. So this right here is the very first trapezoid. Plus the second trapezoid is 1/2 times the height 1 times the quantity base 1 plus base 2. In this case, y2 plus y3. Plus, and I'm sorry, it's going to 2 lines, the next trapezoid, the third one here, is going to be 1/2 height 1, and then it's going to be a base y3 and y4. So y3 plus y4, and then the very last one will be 1/2 height 1, and then I'll have base y4 plus base y5. So y4 plus y5. Alright, so now let's see what's common in everything. I have a 1/2 and a 1 that's common in everything. So let's factor it out. So 1/2 times 1. And then what's left over, I'll put it in giant brackets. Well, I'll have y1 left over, a y2 left over. And I pulled out the 1/2 and the 1, so I'll have another y2 plus y3. And then from this term, I pulled out the 1/2 and the 1, so I'll have this y3 and a y4. And then from this term here, I'll have a y4 and a y5. So now, what I'm going to end up having is T4 is going to end up being 1/2 times 1 times the quantity y1 plus, well, there's 2 copies of y2, so 2y2, plus 2 copies of y3, so 2y3, plus 2 copies of y4, so 2y4, plus 1 copy of y5. And even though we do have one number that's going incrementally up by 1 every time, this 1, then 2, then 3, then 4, it's not going to be the exact same formula to be able to condense this portion down here to summation notation, because only these middle terms, notice, are multiplied by 2. They're doubled. So the very first base 1 or y1, and then the very last base or y5 here, so y1 and y5 are only used once, so they're not doubled. But every single one in the middle, y2, y3, and y4, you'll notice are doubled. And that's going to be the general formula. So we can finish out this problem here. We're going to have 1/2 times 1. So y1 in this case, remember the function was a square root function, so it's the square root of 1 plus 2 times the square root of 2 plus 2 times the square root of 3 plus 2 times the square root of 4 plus the square root of 5. So notice we did not multiply the first one and the last one by 2. So then the rest of this would be plugging it into your calculator. And we're going to get out 6.7643 as our trapezoidal approximation. So we'll take a look at the general formula here in a second. I want to quick focus on the fact that this 1/2 will always be here because of the trapezoid formula being 1/2 times the height. And then notice the height in this case, 1, is really our delta x. So it's going to be 1/2 delta x. and then all of the middle heights will be doubled, and the first and the last one won't be doubled. It's going to be the general formula. So just that focus on the delta x being pulled to the front, as well as the 1/2 from the formula for the area of a trapezoid. One other quick thing is that if we were to instead have been told to approximate the area from 0 to 5, then the very first trapezoid, and I say that really with sort of quotes happening, because between 0 and 1, if I look at the first height, well, the first height is 0. So if I connect y0 and y1, I then have a triangle. But that's okay. So I just wanted to make that point that if I'm using a trapezoidal approximation, if I ever have a height that's 0 for one of the bases, then I might end up with a triangle, and that's okay even though we're doing a trapezoidal approximation. Just like it's okay if we're using a rectangular approximation, if the rectangle happens to have no height, then that's not a problem either. It just doesn't get included as part of the approximation. So both of those things are just subtleties that might get students confused a little bit, but it's absolutely okay to happen. So let's look at the formal rule here. The trapezoidal rule says that the nth trapezoidal approximation for the area bounded by y equals f of x and the x-axis between a and b is given by t sub n equals 1/2 delta x times the quantity y sub 0 plus 2y sub 1 plus ... 2y sub n minus 1 plus y sub n. So again, a little heavy on notation. We can't condense it down to summation notation because of the 2's, but you'll see it's really 1/2 delta x, and the very first base and the very last base as heights are not doubled, but every base in between is doubled. And the delta x formula is still b minus a over n. And then to give a more explicit way of finding these y sub numbers, so y sub j's, we're still using that f of a plus j delta x formula for each of those function value heights. And a really important note to remember is that the trapezoid approximation is the average of the right and left endpoint rectangular approximations. So in other words, if we've already gone through the trouble of finding the right and the left-handed approximation using n rectangles, if we take those two and add them together and divide by 2, we found exactly the trapezoidal approximation. So we wouldn't have to go through the process of using this formula if we already had the right and left-handed approximations. Alright, let's do another example. Let's use the trapezoid sum to approximate the area under f of x equals x squared between 0 and 2 with 4 trapezoids. So let's go ahead and draw that. So we know what the x squared function looks like. Rough sketch here. We're only interested in what's going on between 0 and 2, so only in quadrant 1 we're interested in a trapezoidal approximation between 0 and 2 using 4 trapezoids. So each of those heights, again the heights are on the x-axis, have to be of equal width here. So let's divide this into 4 equal intervals. So halfway would be 1, and then each of these will be of width 1/2. So this one here will be 3 over 2. So now if I wanted to construct each of these trapezoids, so draw them out, and this is a question that would appear on a test or a quiz, is actually drawing out the trapezoidal approximation. So over the first interval from 0 to 2, here is a case where the height of the first base is actually going to be 0, and then the height of the second base will be up at f of 1/2. So my first trapezoid is really a triangle. So that's going to be my first one. And then between 1/2 and 1, my first height or base is going to be f of 1/2, but my second base is going to be f of 1. So I'm going to go up to the function there and then connect those two with a straight line, and that's my next trapezoidal approximation. So this point here was f of 0, this one was f of 1/2, this one was f of 1. And then between 1 and 3/2, I'm going to go up to the function at 3/2, connect f of 1 and f of 3/2 with a straight line. So here's my f of 3/2 point. And that's a little bit too messy. so f of 3 halves. And then finally I have f of 2. So if I go all the way up to the function at 2, and I connect these 2 points, that's going to be my last trapezoid. So up here at f of 2. Just a rough sketch. Sorry, it's kind of messy. So that's what we're trying to do, is we're trying to find the area of each of these trapezoids, one of them specifically being actually a triangle instead of a trapezoid. So if I use my formula here, I'm going to find T4. So it's going to be 1/2. 1/2 is always there. 1/2 is not delta x because the formula is 1/2 delta x. So delta x in this case is going to be 1/2 as well. So I can solve for it. Delta x is b minus a, so 2 minus 0 over n, which is 4, or 1/2. And we also found it by dividing the interval from 0 to 2 into 4 equal widths. So we're going to have 1/2 times delta x, which is 1/2. And now here's where we start using the very first height. So that's going to be f of 0 plus, and now I double the second height, so 2f of 1/2, plus I double the next height, 2f of 1, plus I double the next one, 2f of 3 over 2, but I don't double the last one, so plus f of 2. So now I can start to simplify. 1/2 times 1/2 is 1/4. F of 0 is 0. Plus, if I plug in 1/2, 1/2 squared is 1/4. 1/4 times 2 is 1/2. Plus, f of 1 is 1. 2 times 1 is 2. Plus, 3/2 squared is going to be 9/4 times 2 is going to be 9/2. And then finally, f of 2, if I plug in 2, I get out 4. So now I can go ahead and keep solving. I can do this in a calculator, but really I can do it by hand. So I'll just keep going by hand. So 2, if I write it as a fraction, since I have, well, 9 over 2 and 1 over 2 is going to give me 10 over 2, which is 5. So 5 and 6 is 11. So what I really have is 11 times 1/4, or 11 over 4. Alright, and in this next example, we're going to use 6 trapezoids to approximate the area under f of x between 0 and 18 given the following table. So the last example, we were given a function, and now we're given a table of values. So we want to end up finding T6 here. So the general formula, remember, is 1/2 delta x. So we can solve for delta x explicitly. So delta x, we can write it as b minus a, so 18 minus 0, over 6. So 18 divided by 6 is 3. Or, again, whenever we have this table of values, we can think about it as if the x values are varying by the same quantity every time. So to get from 0 to 3, we need to add 3, 3 to 6, add 3, 6 to 9, add 3. So that would force each of these to be the same width. So this is with 3, this one's 3. All of these are going to end up being 3, and then how many of them are there? There's exactly 6. Then that told us what my delta x is going to be. So 1/2 delta x is going to be 3 times the quantity. So now what I have to do is, so if this is my very first trapezoid from 0 to 3, then I take the height of the first one, and then I take the height of the second one, and I add them together. But remember what this is going to end up doing when I do the second one. I take the height of the first one and I add it to the height of the second one. So the general formula says I take the very first height and only put it down once. So f of 0 is 2, so I would only write down 2 once, plus every middle term. So all of these here in the middle are going to be doubled. So 2 times 5 plus 2 times 3. So now I'm on 5 again. So 2 times 5 plus 2 times 7. Ran out of space. Plus 2 times 2 plus, and the very last one, just like the first one, does not get doubled. So now here we're going to have 3 over 2 times the quantity 2 plus 10 plus 6 plus 10 plus 14 plus 4 plus 1. So let's try to add things up. 10 and 10 is 20. 6 and 14 is 20. So that's 40. 45 and 2 is 47. So we have 3 over 2 times 47, which is 70.5. So that's our trapezoidal approximation using 6 trapezoids, but I want to change the problem for a second. I want to change it to use 3 trapezoids. So let's just erase what we've done here and then try to think about how using 3 trapezoids would affect our answer. So now we're trying to find T3. So first of all, the 1/2 stays. So it's always, with the trapezoidal approximation, 1/2. So now I need my delta x. So if I use 3 trapezoids, this time I'm not going to use the delta x formula. Let's just try to think about it. I need 3 trapezoids of equal width, or really height, because the height is on the x-axis, but I need 3 trapezoids. So I want to go from 0 to 6, then I want to go from 6 to 12, and then I'll go from 12 to 8. So in each of these cases, I'm going an equal amount, and that equal amount is 6. So if I use 3 trapezoids, then my delta x quantity is going to be 6. And so now, here's where it gets tricky. I don't care at all about these midpoint values, so I'm just going to cross them out because I'm not trying to find a midpoint approximation. Remember, trapezoid approximations use really the endpoints. In fact, they use the middle endpoints twice. So the very first endpoint's only used once, so we'll put down that 2. And then we jump to the next one, which is doubled. So plus 2 times 3. And then the next middle one again gets doubled. So plus 2 times 7. Plus the last one does not get doubled. That's just 1. So 1/2 times 6 is 3. And now here on the inside I have 2 plus 6 plus 14 plus 1. So I have 3 times the quantity 23. Or I'm going to have 69. So my trapezoidal approximation, using only 3 trapezoids this time, ended up giving me a value of 69, which is pretty close to 70.5, so it's not out of the ballpark, and my answers do seem like they could be feasible since they are close to each other and they are approximating the same function.